Thank you very much. Can you all hear us okay here? I'm excited to be here. Today we're starting with a provocative question. Is AI hardware all about software? We've seen an explosion of applications of AI and machine learning over the last decade, really driven by the availability of data, the availability of amazing models, especially with deep learning, and of course, tremendous hardware advances starting from GPUs, but now driving towards specialized hardware. And together, these trends have enabled us to do amazing things. It's kind of hard to imagine, but today we're interacting with AIs every day, all the time, and we often take them for granted, which is exactly what we want in our field. We want it to feel like an integral part to everything that we do. And it's important for us to think about how to do that more efficiently, more cost-effectively, and in a more ubiquitous manner. And that's where the combination of AI hardware and software can do amazing things. And to talk about that, we have three amazing panelists here with deep experience both on the hardware side and on the application side, bringing those together to have impact in the world. So in the middle here, we have Professor Luis Ceze, who was a colleague of mine at the University of Washington, and now is active as a co-founder and CEO of OctoML, which enables businesses to seamlessly bring machine learning models to production, accelerating them across a wide range of hardware targets. He has worked on machine learning and computer architecture for many years, but he's also pushed the boundary into new technologies. For example, through the Molecular Information Systems Lab, they've led pioneer work in the intersection of computing and biology with applications like DNA storage, which is super cool. So thank you so much for joining us. On the far end, we have Sakya Dasgupta, who is the founder and CEO of EdgeCortix, which designs edge AI systems for low latency and significantly higher energy efficiency, which is something that we really care about, and they're exceeding the results of CPUs and GPUs today. Prior to this, he was a senior research scientist and executive lead at the embodied robotics group at IBM Research. With deep expertise in AI, he brings the connection between AI hardware in an exciting way to this panel. And right next to me here, we have Jian Zhang, who is the director of machine learning at SambaNova Systems. He leads the Core ML team, which brings deep learning foundations to SambaNova's large-scale enterprise AI solutions. Together, they're thinking about both hardware and software innovations and the co-design in this emerging field of accelerated machine learning. Before joining SambaNova, Jian got his PhD in ML from Standford University, working in NLP and machine learning systems. Again, this combination of AI expertise and hardware will be really important to the topic of today, which is thinking about AI hardware acceleration and the relationship with that and software. And to start us off, I've asked our panel to think about what are the most mission-critical applications of AI today where hardware acceleration will be indispensable. So maybe in the order of the introductions, I'll ask Luis to start.
All right, well, thank you. So I think it would be a popular answer. Honestly, I think it's everywhere, both in the edge and in the cloud for different reasons. On the cloud side, you care about extreme peak compute to actually train large models, extreme data bandwidth you can actually read and deal with very, very large models, and also very, very low cost to train large models at a reasonable time to solution. So that's on the cloud side. And then on the edge side, it's critical because you need to have low latency for interactive applications, and it has to be low energy. And I just can't imagine how you can do both of these things without having hardware acceleration. And in fact, I feel hard pressed to imagine any significant advances in machine learning is not going to come, motivated or done together with hardware innovation. So,
thank you, Sakya. From your experience with EdgeCortix and thinking about, beating CPUs and GPUs through acceleration, where do you think that's going to make most difference today?
Yeah, so I think I take a little bit of different approach here, and I'll talk about the edge in a bit. That's where we are. But the way I think about this question is more about how far we can get purely with software acceleration rather than AI hardware acceleration. And I think purely even with software, we can go a very long way in the data centers where you don't have as much of a fragmentation that you see on the edge. In the edge, you have very different types of devices, applications, form factors, power requirements, latency requirements, connectivity requirements that you don't typically have those constraints in a data center. So purely software can take you very far away. And we have seen examples of that already with platforms like OctoML, amongst others, from an open source standpoint, TVM. Whereas on the edge, you really need to have the right combination of software and hardware acceleration purely because of that fragmentation. I don't think we'll see any single winner emerging. Because of that fragmentation, you got to cater really from a platform standpoint or a system standpoint and bring both software and AI hardware acceleration together, but more so innovate more equally on the hardware side as much that you might not do on the data center side purely.
That makes sense. I think, Jian, your experience with building solutions with machine learning, probably a little different, right? The perspective from your side. So maybe you tell us about what applications you're seeing from the other end of the spectrum.
Yeah, so basically if you think about what the AI acceleration is solving is that first you can make something that's already working to be faster and better, right? The other aspect is like how you can leverage the new technology to make something that you cannot do or easily do before to get an emerging capability in the new era, right? So if you try to think about those like large language models which people are trying to put together a solution on, basically people are looking at enable more broader audience or industries to be able to leverage those technology. And you can imagine those things are not just enabling them to run faster or enabling them to achieve like a 1 or 2% better accuracy, but it's changing the paradigm they do things in their AI development, right? For example, like how you can use these large language models enabled by these AI accelerations to enable you to say, I only have like one or handful of models, but supporting many of the tasks, and potentially like how I can, robustly or easily to deal with low-level case with these large language model support.
Yeah, great. There's a huge spectrum between the edge and large language models in the cloud. Jian, let's get a little geeky now to start out with, and let's talk a little bit about the systems aspects of this. And these are hybrid systems. They have lots of cross-platform complexities. They have lots of low-level hierarchy complexities. What do you see are some of the systems design challenges as we think about creating these applications of AI in an accelerated fashion?
So what I would say is like, actually, if you think about the type of solutions that we are targeting is like, which is used for broader like data scientists, what they are looking for is really an ease of use entry point. And basically like, there are a lot of things to be hidden into a single box to enable that to happen in a button clicking fashion, right? So think about like how we can build a large fleet of system. Think about how we can have the expertise to do the performance tuning. Think about like how we can have enough ML like expert to put in the action to make this model useful for different people, how to manipulate data, all these stuff. So basically, really what I see is like emerging like a vertical solution to accommodate all these expertise if like your targeted customer is more on the end of like a high level like data scientist users.
Yeah, if I may add to that, I think along with that, those vertical solutions, one of the critical aspects of the systems requirement, whether you're going across data center or the edge, that there is inherently a heterogeneity that exists alongside those platforms. Many of the solutions that we are deploying today, whether that's the software or the hardware piece, is spanning across various different types of processors that needs to coexist. So from a system aspect, we got to really think about memory. You got to think about whether that memory is at the data center level, and it's probably going to manage very different types of workloads, whether it's the compute element at the edge, and how efficiently it's talking to memory at the edge is going to be very different from how it would be at the data center. And then, as I talked about that fragmentation, it could be CPUs working together with other types of processors, GPUs, and then now we have, of course, we are making our own AI accelerators, very different silicon by itself. All of that needs to coexist. And I think that's the system challenge that we really, from the software standpoint, going back to the theme of this panel discussion, needs to solve if we want to really build efficient systems at the edge or at the data center.
Okay, the quick thing here. So I think we tend to be a lot, compute-centric here, but I would say that every time you make a compute engine really, really fast, a natural next question is like, how are you going to feed data to it? So I feel like a big systems challenge is like, how are you going to increase, compute throughput in a way that you're going to keep what you need in terms of compute to bandwidth ratio, right? And then have the right bandwidth also on the storage side if you're going to go and read training data from there. And then you have the systems programming challenge of keeping everything busy all the time. Otherwise, you actually have an unbalanced system, right? So like just keeping all of these compute, storage, network bandwidth ratios all right, and busy seems like one of the big challenges system-wide.
So we talked about the range of challenges, of systems challenges. Another question on my mind is the plethora of machine learning models and workloads. So a little side story here. I was meeting with a new PhD student at Stanford that's going to rotate with me this coming quarter. And she was saying, I'm very interested in this paper I just read. It's an old paper, came out last year. But maybe we can still do something in the space. And I'm thinking, wow, from my perspective, last year is a blink of an eye, and so machine learning is evolving rapidly. It's not just about the wide range of hardware targets below, but also the fast-coming plethora of models and innovations and just an incredibly fast-moving field. I can't keep up with anything that's going on. And amazing things that my colleagues are all inventing. And so maybe I'll start with Luis. How do you think about the versatility of the stack here and the approaches to deal with hardware targets growing, models growing, and still reduce the time to adoption of machine learning in the real world?
Well, I have a lot to say for that. So luckily, I have a half hour to answer.
26 minutes and 42 seconds.
Well, no. First of all, it's pretty clear that people care a lot about time to deployment, right? So especially from a systems provider point of view, your customer is going to come to you like, here's a cool new model, say, Stable Diffusion. Can you get it running on your system tomorrow? And then realize that, hey, machine learning models today are not like software engineer that can just compile and try it and it works, right? You have to just a huge amount of infrastructure, either in the form of operator libraries or compiler infrastructure or just the rest of the system. So I'd say the only way we can address that, one is not rely on manual engineering to actually get your first model running. So you have to build your system software stack with automation in mind from the get-go. Right, so that's why when we're biased, we take a compiler-based approach where we want to see a way, we want to show that there's a path from a model to a very efficient binary in a fully automated fashion. That yes, performance evolves over time, but at least you get something running very, very quickly. So the way you get versatility then is, take an automation-first approach. So compilation is less about compilation, more about search, I would say, of good solutions. And then second, given the cross-product of models, frameworks, and hardware targets, for any solution that would say would be broad enough, I just can't imagine something that would not be in the form of an open source, approach with a significant community that helps this be future-proof. Otherwise, it's always going to be on your toes. Like if you're a hardware vendor, you're going to have to keep increasing your operator library team, ad infinitum to be able to support, the plethora of models. So by being part of an open source community, you can, at least I see a sustainable path forward. So.
Yeah, I mean, if I may add to that, right? So I think the way we think about that question is there are two aspects. And as a company, we are doing both software and hardware. So I'll touch upon the hardware piece first. I think building systems or hardware that is future-proof is incredibly hard, especially when models are changing so rapidly. One way to, the way I like to think about this is that building hardware, which is a lot more operation-centric rather than operator-centric, is the right way forward. What do I mean by that? Rather than building a silicon that is focusing on, let's say, a convolution type of operation, or let's say a recurrent neural-like type of operation, if we build the fundamental building block, whether that's Max or it's neuromorphics, event-driven, I think that's the right way to go, where we are creating a hardware that takes into account the fundamental operation that we would perform, because that really does not change, or it changes much slowly as compared to the different types of operators that we would invent from a machine learning perspective. On the software side, I think alongside that approach on the hardware, we need to imbibe a lot more co-design or a co-exploration approach, where while we are kind of looking through or searching through the space of models, we should be taking into account what are the limitations or constraints at the hardware level. It could be memory, it could be data movement bottlenecks, it could be latency, it could be power, it could be area of the silicon itself, and that allows us to be a lot more future-proof, where we are actively designing models that are better suited for hardware, and then vice versa.
Yep. Yep. So I think I really want to add on Sakya's points, right? So what he's really talking about is like raising the level of abstraction when you are looking at this fast-changing field, right? For example, like you can see every year, every day, there are so many different like new machine learning papers with different like model structures coming out. But actually, there's a certain type of like abstraction that we can extract. For example, people focusing on transformer models, people focusing on like a convolution model still in some areas, maybe Jian models. Like there's a couple of like mainstream of the stuff. This actually plays like the middle layer to give the software builders an opportunity to say, hey, you can focus on mainstream of the things and make sure those things can work well for a pretty wide range of applications and customer need. Instead of like directly solving the entire universe. Okay. Yeah.
So a quick follow-up before we go to the next actual question. Do you think, though, the AI field stable enough to put down, transistors on silicon for some of these? I mean, I can see, sorry, I'm going to monologue for one more second, Luis. I can see you talked about convolutions as an operator. Convolutional neural networks are pretty stable and they can be useful in many places. But if we think about the growing and fast-changing field, do you think that's stable enough to put, silicon on a chip? Luis, you're dying
I know. I'm dying to say something here, obviously, because I'm a computer architect at heart.
Tell me why I'm wrong.
I do mostly software in my life. So, I honestly, you have a pretty tough decision to make, right? So because on the one hand, you want to be the best you possibly can be at something that's of high value to your customers, such that when your chip hits the market, you're actually gonna, you'll be able to make money off of it, right? So, but if, first of all, it takes too long and you miss the boat for that model, then, your solution lost value. Or if you build something so specialized that by the time it's ready, again, the model won't be relevant anymore. So you have to find a way, find just the right balance of how do you get benefit from specialization without being trapped by it. So, and I can't think of another way other than just really being very, very principled about what goes in hardware, what goes in software, and then co-designing them together in a way that you actually have enough flexibility, enough movement to accommodate model changes, right? So anybody would be nuts to say they're going to bake something in, so directly, right? So,
if I may add to that,
yeah, please.
Right. So, like we are running a company as well, right? So we absolutely think about what we can bring to market very fast, right? The way we have thought about this is, rather than building silicon that is, operator centric, if we can build silicon that by itself is or contains some degree of reconfigurability. Now, whether that's, in the academic world, we have called it a CGRA, we have called it various different names, but essentially it boils down to, can we have some degree of reconfigurability that is not as fine-grained as an FPGA, where you're sacrificing, let's say, efficiency, but you can still preserve some degree of autonomy when the model changes or the operators changes. That's the approach that we took internally, and then build or co-design the software on top of it, such that we are a little bit more future-proof without having to wait for years to bring that silicon to market.
But you still need to make a bet where you put this diode here, right? Otherwise, you have a pretty big room there in between, like how much configurability you have versus the overhead that you pay for it, because if you're going to be judged by efficiency and versatility together, you have to make bets there, right? So.
That's exactly right. Yeah, I absolutely agree. I think at some point we do have to agree on how much of reconfigurability, whether it's fine grain or coarse grain, But the point being that, to me, it seems it's obvious that you've got to have that feature at the silicon level to be able to be future-proof. If you have a silicon, which is, let's say, an application-specific, dedicated for only one type of operator, a set of operator, well, it will work for a few years, but then, and as we already heard, in 1 year, your models have completely changed. It takes a lot longer to build silicon, so it would be obsolete. And I think that's a requirement. Of course, the choice of how much of a degree of reconfigurability we add, there are different choices, and that's where, again, co-design comes in. The broader we can cover the existing set of models, we feel that's the right way to do it, because you would be more, you will cater to a lot more applications today, but we do have to make a choice at some point.
So I'm going to open it up in a moment for questions from the audience. So if you have some, start thinking about those. But before I go there, I like where we're going for a little bit more, debate here. So let's take another step in that direction. Sakya, this is for you to get started. What's the difference between the data center and the edge? And where should we be really investing?
Yeah, I think that's a very open-ended question. So what's the difference between the data center and the edge? I think there are various different ways of thinking about that. The way we like to think about that would be from really an application perspective. I'll give you an example. So let's take a non-AI application, Google search. Okay, I'm saying Google, that's the most prevalent, you could search anywhere. But let's say search in general. And if I'm searching for images, the way I retrieve that data, I have a lot of luxury. I can batch a lot of that data. I can have a database of all of those. And as a consumer, I don't realize the amount of work that it's taking to retrieve that data. But I'm scanning through a huge amount of data already, which has been pre-compiled or pre-documented in a database. On the edge, you don't have that luxury in most cases. Let's take the example of a car. You would have to make a decision right that second, or sometimes in milliseconds. That means real time becomes critically more important. Or in the language of machine learning today, we don't have the luxury to batch data. You're really going after low batch sizes, batch one really, where latency becomes the most critical factor. That's the fundamental distinction that we see between an edge and a data center. A data center typically is more throughput-centric. You have a lot more luxury of batching data, running across the data, whether that's a recommendation system. Very rarely you would see a recommendation system running on the edge device. Whereas on the edge, you're really latency-centric, and then power becomes a factor because you are not confined to one particular area. Typically, edge would be mobile, which is mobility. That means you now have fundamental restrictions on the form factor, battery operated in most cases. So those are few fundamental differences that clearly distinguishes the data center and the edge.
Jian, do you want to jump in?
Yeah, for sure. I can talk a little bit from like the application perspective, right? So I think really like if you try to think about the model developers, the machine learning folks, sometimes their decisions are constrained by the hardwares they have, right? So basically, for example, just as a Sakya side, for certain type of workloads, because of the constraints, they need to put a big recommender models into data center, right? Maybe like if there's a powerful enough edge device that could someday support this type of large workload, there's still like incentive for them to do it there. So I think like there exists a lot of like system constraints that we are trying to break through these days to make like the difference between data center and edge diminish. But I think there's a long way to go there.
Any questions from the audience here that we want to add?
Can I just add a quick thing here?
Of course, yeah.
Can't resist. So I think there's something called speed of light here that has a, you can't change anything, but you cannot change the speed of light. I feel like this put a fundamental restriction on how you think about things that you fundamentally have to run on the edge because you just don't have able time to just go to the infrastructure. Or if you're thinking about the kind of applications that I find exciting on the edge, would normally require either one, level of reliability that you probably want to do a lot of it locally anyways because you want to place a bet on the infrastructure. And then two, you can't rely on, having truly instantaneous communication, right? So.
If I may add to that, well, maybe, there's a question, okay.
Yeah, please.
Yeah, actually, I have two questions, if you don't mind. First is probably for Sakya. So I like the thing that you mentioned about future-proof in the silicon. So how do you think that future-proof technology would be.
Could you repeat the question? How we will achieve future-proof?
Yeah.
What do you think your approach is in terms of solving the problem?
Yeah, I think there is no one answer to that question, right? So the way we think about it, and it may not be right, but our approach really is, one aspect is having some level of flexibility.
Right.
Like the brain, as we understand, is really malleable, right? It's plastic. Now, how do you reproduce that in today's generation silicon without having to create a brain-like substrate? Is to add some degree of reconfigurability, dynamic behavior. That's one aspect that we took in our approach to build silicon from the ground up that has that dynamic aspect, that can live longer than today's hardened blocks that would work only on one type of operators. The other way that we think about is, from a purely hardware perspective, it's really to take into account the chiplet idea, where you can now scale up significantly better rather than having to build very, very large scale compute blocks. Perhaps we would differ on opinion between SambaNova and us on that. So our approach is, you start from the edge with smaller compute blocks, could be as a chiplet, and then use that building block to scale up into larger systems, rather than take the opposite approach where you start with a very large scale system, a large scale processor, very difficult to scale it down because you've already made design choices that go into the complexity of multi-core systems. The other way you can build future-proof systems is, even in that chiplet approach, you start with single core being a focus. So what we did is that we focused on having single core systems managed a lot more easily. It's a lot more easier to build software or compilers for single core rather than for multi-core. And for the edge, it works really well because you can achieve low latencies and then use that as a building block to build large-scale systems. Those are some ways that you could do that.
If I'm follow up on that. So when I step back and think about the previous company that I co-founded, Turi, we really tried to make machine learning more accessible to more people. And it's already hard to program a CPU, then a GPU, then a specialized piece of hardware. I'm wondering what kinds of personas you're thinking about as who you're targeting as the users of the systems you're building, and how do we make sure that we're still making machine learning accessible to every developer who has an idea that's going to change the world? So, yeah, I don't know. Who wants to start?
I can start with. Yeah, so I think really the question about which personnel you are targeting at is really interesting question, right? For example, for us at SambaNova, when we are building this vertical solution where it includes everything, we are really targeting at those end customers, the high-level data scientists. What they actually expect is just a few click through, and then they can get some challenging workloads runs automatically, and they just interfere with very minimal operations that is not beyond their understanding of the underlying technologies. So basically, the targeted personas decided where you set the abstraction APIs to expose to them. And I'm pretty sure Luis have a different view on their targeted personas, right?
Yeah, so we think of, let's think about our Apache Tensor Virtual Machine projects and open source, end-to-end model in binary out, right? So we think of three personas. First is the ML system software engineers. So these are the folks that hardware vendors would hire to make sure that their hardware has a software stack. So from that persona's point of view, what we want is the ability to extend to a new hardware target as quickly as possible without having to build stuff that they shouldn't focus on, right? So that's the first persona. The second persona on top of that in the stack is DML engineers. So these are folks, I would say, they watch the new machine learning innovations, and they want to make sure that, hey, I want to get this new model going running in this new infrastructure because it's going to give them an advantage, innovation advantage to integrate that into applications, right? So what this persona cares about is the ability to, one, quickly support a new model, and then two, quickly make use of the stuff that the ML system software engineer exposed, right? So that's second. The third persona is folks that can focus on create the model and not worry about the infrastructure at all. And this is where we at OctoML focus with CVM together with our platform is enabling data scientists to really get a new model and very quickly run on all the hardware that they would possibly want to run their models without worrying at all about any system parameters. So in that case, what we want to focus on is abstracting away all of the hardware details, right? So.
Another persona that we experience, if I may add, alongside those three personas, is if you're deploying a solution in production, system integrators are incredibly important. Now, system integrators typically don't think about the model. They are really agnostic to that. They are agnostic to the hardware that you're deploying as well. But they are building a system together. And in many cases, AI or machine learning, and we tend to forget that, it does not exist in isolation. You are putting an AI or machine learning solution that would coexist with some existing application. For example, it could be a networking solution, it could be a 5G application, where you're adding some level of intelligence on board. So it's very important that whatever software we create, it caters to even those system integrators from a platform perspective. We try to take that approach as much as possible. That enables the system integrators to have some level of control, leaving out all the chip level or the hardware level complexities outside, leaving out all the machine learning complexity outside, rather than then having to worry about whether it's a PyTorch model or it's a TensorFlow model. Can they build systems that bring, let's say, a CPU, a GPU, or an accelerator together, as well as work with APIs that are easy enough to integrate with a networking solution and add intelligence on board that?
Great. Other questions from the audience here? Yes, one over here, please.
I was going to extend that to this question. Sakya,
Can we give somebody else a chance to give a chat? Then we can come back. Thanks.
Title of this session is AI hardware is all about software, and I want to ask you a question about among all the hardware companies out there, as currently now, who would you give the highest score for in terms of positioning-wise? They're leading the pack. I know a lot of management from like Intel, NVIDIA, GrabCore, they also have said that the software is really, really important. But for hardware companies, it's really, really difficult to do everything at the same time. But some companies are doing better than others. So who do you think is leading the pack, and who do you think is actually behind the pack? It's kind of It's a kind of tough question to answer, but I want to get your opinion on.
I'll probably give a biased answer, so I should go last.
I'll let folks be politicians and answer the questions in whatever way you think most. So why don't you take it along? Why don't you start, Sakya?
I would say, I don't want to say that we are leading the pack. I'll tell you how we are approaching this, right, ourselves to differentiate us from the existing solutions that exist out there. When we started off with EdgeCortix, we knew that we had to build a different silicon from the ground up, but we started with software first. And it's very apt that we're talking about AI hardware is all about software. We started with the software, and we started with that system question, is that if I'm going to build a silicon, it's not going to exist in isolation. It's going to work alongside existing processors. It could be CPUs, GPUs, etc. That was the first principle. The second principle was, and we touched about that a little bit, how do we build something which is more operation-centric rather than the operators? So we added reconfigurability aspect into the mixture so that it's more future-proof than existing silicon in the market. And the third thing we did is one of our earliest patterns was co-design. Can we start searching the space of existing models while being able to search also, to a lesser degree, but the design space of hardware. So if I have a piece of RTL that I'm writing to design a processor, can I search while searching through constraints of accuracy of a model? At the same time, can I add a constraint of what the area of that piece of silicon should be? Can I add a constraint of what the memory requirement should be? And then co-design that process. We believe that has helped us bring a lot more efficient silicon to the market that effectively is showing a lot better efficiency than some of the others.
No, think I like to be Switzerland here and be neutral. So here's how I think about it. Diversity is good, and it's always going to be there. Like, you're actually creates the ability of, multiple solutions, especially on the hardware end, to actually pop up and be viable. And then from the end user point of view, allow them to give them choice. Right, you give them choices, the ability to like, here's a model, find out what is the best hardware they should run on, and then let the best option win for that. And the reason I think that can be viable and still have multiple solutions coexist is because people have different needs, and there's enough diversity, from the end user point of view as well to have multiple options coexist. So, the way we think about this at OctoML is really to give folks choice, where it should run, right? So without having to worry about the complexity of deploying, and then helping them make the right choice. Right, so when you have a model in, go and choose what's the best hardware to run on in the cloud, right? So,
yeah, and also if you try to think about the coexisting of so many different hardwares, very important or interesting aspect is that you can think from the application perspective, right? Like what a new thing can enable you to do that you cannot do easily before, right? It doesn't mean like a 100% replacement, but it means expanding your boundary about imaginations and about what you can do with something new, right? And then, I pretty much feel like, the human beings' exploration is just, make us step forward. You find something interesting, you keep expanding, there's a new word coming out from there. Yeah.
And,
quick question.
Can I add one more?
There's a quick question from the audience.
Oh, okay, sure.
And then we'll...
Yeah. So I want to follow up what Luis said a little bit earlier. He mentioned speed of light. So what is the speed of light for software, which is today's session here? What's the ideal software for AI application developers?
Well, I'm hugely biased. I know you're looking at me, but I would say that you have to show an automation path. As soon as you have a model, what I want is to be able to treat machine learning models as if we treat any other piece of software. Where there's always a piece of software, you can run it on a target hardware. There's a tool to do that. It's maintained. That's always ready to go. And then make it very easy for folks to integrate that into applications. So I don't think it's viable for us to have all this innovation being latent there and take weeks or months for a model to be deployed, right? So
we're going to run out of time. So I'm going to let one person ask a quick question. We're going to have 1 minute to answer it, and then we'll have a closing question.
Yeah.
Okay, one quick observation, which might be not so great for the hardware people, which is I don't actually think the hardware matters. The hardware, we install it, it sticks, we use it for what we use it for. If it has a fixed set of capabilities, big deal. Software is forever. I think the API choices you make now, you never get out of. Like we bend our TPUs to work around Borg. We still run TensorFlow and XLA on all generations of TPUs. Things in early XLA API design stuff is with us forever, and you can't undo it. So I'd love to hear commentary about that. Like, don't worry about making the wrong decision and generalizing your hardware. Worry about the wrong decision and generalizing your software.
Great, and you're saying this because you don't expose your ISA, because if you did, you had the same problem, right? So.
Yeah, I think that's a great point, and that ties back to the fact that it's very important that we open source, and we talked about that a little bit. So on the software side, it's a lot easier to open source, right? And that has been the challenge. So we are seeing some great aspects of an open source compilers building on top of that. On the hardware side, it has been more difficult, right? It's incredibly more difficult to convince a hardware company to go ahead and open source their ISA, right? So I think depends on the mix, but taking at least companies that are taking the approach where they are adopting open source community, that enables that to be a lot more future-proof, whether it's software or hardware. Software is, in my opinion, a little bit more easier to go in the open source direction as compared to hardware.
We should continue this at over a drink later, but I do think you could say that software can be ephemeral too now. The level of innovation, the churn could be so fast that if you abstract away and you create the right tools for automation, not even the software stack has to be that rigid.
All right, I'm going to take the prerogative of the moderator. Last question, 10 seconds each. What is the big thing that's going to happen 5 years from now that's going to make a big difference in this same space that we're in? Jian.
Yeah, I guess I'll take my consisting standing point is that like in 5 years, I want to see a lot of the emerging capability from like a new generation of the models being democratized through the AI acceleration to a lot of different industries.
All right, 3 quick things. Blurring of inference and training. I think they'll be like more and more blurred. Second, embracing dynamic behavior of dynamic tensor shapes, dynamic control flow, and so on. It's going to start looking more and more like like CPUs in general engines. And then third, embracing new technologies for real. Like for example, maybe code logic for training the data center would make sense. And I feel like in 5 years, this line of sight of actually being much more adventurous with new compute technologies, especially in the data center. So.
Yeah. So I agree on one of the points, absolutely. So I think, I would say more than one, but one more so, where I think we'll see a lot more continuous learning coming in and blurring that line between training and inference, with the edge having a lot more ability to learn from the data better, rather than purely being passive inference devices. At the same time, we also think that in the next 5 years, you'll see a lot more better kind of blurring the lines between different types of hardwares. So taking a lot more platform-centric approach will become a lot more popular, and we'll see a lot of the workloads that are purely on the edge side, or this divide that exists between data center and the edge, slowly blurring away.
All right, let's thank our panelists here.